Well, problem 24 about the chain letter may have been fun to do. Problem number 25 is couched in a way that you're more likely to see this when you go into an algorithms class. Look at number 25. It says a certain computer algorithm executes twice as many operations when it is run with an input of size k as when it is run with an input of size k minus 1. That means it's doubling each time, right? When the algorithm is run with an input of size 1, it executes 7 operations. How many operations does it execute when it is run with an input of size 25? Okay, first of all, is this arithmetic or geometric? In other words, are we adding something each time, or are we multiplying by something each time? Well, we're multiplying by something each time. We're multiplying by 2, so this is a geometric sequence. It's expressed recursively this way, where we multiply by 2 each time, and it's expressed this way, where we can take our multiplier to a particular power to figure out what this is for the explicit formula, such as the 25th time. So here is our recursive formula. The algorithm, when it is running on its kth time, it's going to be 2 times the one before it. So the first time it runs, and I'm using 1 because it said first, a sub 1 is equal to a 7. So a sub 2 is 2 times 7 or 14. A sub 3 is 2 times 14 or 28, and so on. And you could do this for 25 times. But do notice, if I express it this way, this is 7. This is 7 times 4, or 7 times 2 squared. So you see, my exponent here on the 2 is always 1 less than the subscript, because I started at 1. So on the 25th time, it's going to be 2 to the 24th times 7. Now that might seem a little bit strange because it doesn't exactly match up with what our formula was. But if we work in the computer sense of this, and we start at 0, a sub 0 is 7, and then it fits the formula exactly. So if you start the 0th case, and you go to case number 24, which is the 25th case, you're just taking 2 to the 24th times 7. By the way, if you pop out your calculator and look at what 2 to the 24th is, I get 16,777 to 16. So you see, even doing a simple operation where it doubles each time is really going to have a massive effect on some operation we do repeatedly. Now if I multiply that by 7, you can see I am getting 117,440,512 operations. Well, what's an operation? Well, you have to look at the clock speed of a computer and figure out how many operations the computer can do in a second, and that would tell you how long it would take this algorithm or this subroutine to run. One of the things you do in an algorithm class is you evaluate different kinds of algorithms and put them into classes based upon their speed, and you see if you can improve on the algorithms to make them run faster.